Hello everyone, my name is Bruna and I'm going to present a part of my master's research entitled On the Numerical Integration in GFEM Analysis for Physically Nonlinear Problems and Cohesive Crack Propagation. Given a brief introduction to the theme, we can mention that the GFEM is an efficient methodology to overcome mesh dependency in fracture mechanics problems, for example. In this case, the numerical integration with the non-polynomial enrichment functions, it might not be accurate when we utilize the Gauss quadrature that is commonly used in FEM. So a possible solution for this case is applying the subdivision of elements according to the crack, when we adopt the traditional Gauss quadratures in each generated triangular cell. When we apply this process in physical nonlinear problems, for example, the change of the integration points, it leads to the loss of the constitutive variables. Hence, the purpose of this work is the proposition of a new transferring method for the historical variables inspired by the nonlocal formulation in order to solve physically nonlinear problems in the GFEM context. In terms of formulation of the GFEM, we have initially the partition of unity and also the enrichment functions, and when associated, they generate the shape functions, GFEM shape functions, and also the generalized approximation of the displacement field when we are dealing here with both degrees of freedom from FEM and XFEM, GFEM. Talking about the cohesive crack propagation, we have some functions to describe the crack, the surface, and one of them is the half-side enrichment function that is considered for the FEM shape functions, and also the interface description according to a signed function, herein presented. The cohesive forces in the crack surface, according to Rawls and Lewis, they might be represented according to those equations for the normal tension and the shear tension. In terms of the numerical integration in GFEM problems, as I mentioned, one of the options for the problem when we have non-polynomial arrangement functions is applying the subdivision of elements. So here we have a mesh with some of these elements crossed by a crack, and when we have the traditional Gauss quadrature, some of these integration points might be overlapped by the crack. When we apply the subdivision of elements, we have some generated triangular cells here, and in each one of them we apply the traditional Gauss quadrature for triangles, and hence we don't have the possibility of overlapping the integration points. Also, it is important to mention that in this process we don't add degrees of freedom to the problem, and we maintain also the accuracy of the integration process. When we are dealing with physically nonlinear problems, the integration points, they store the history variables during the loading. But with the subdivision of elements, the original integration points, they are replaced by new ones according to the generation of cells. So we lose the constitutive variables history. Hence, we can adopt some alternative to circumvent such issue, and some of them are presented in PETSEC and Gerais. Well, the proposed transferring method herein presented is inspired by the nonlocal formulation, in which the stress in one point is related not only to its own state variables, but also to the state variables distribution in a region A around such point. Here we have the nonlocal counterpart of a generic field F, and it needs to take into account a weighting function that here we are going to consider the Gaussian weighting function, and also the coordinates from the surrounding integration points of the region A, and the coordinate of the point in which the function, the nonlocal function, is being computed. This is the Gaussian function, where it considers the distance between the points and also the radius of the nonlocal region A. For these work purposes, this region contains only the integration points from the element in which the transfer of state variables is performed, and the set of points with S coordinates is the set of old integration points from the considered element. Here we have an example of the process. So, firstly, in an element containing the traditional Gauss quadrature, and then when the crack crosses it, the subdivision of elements is applied, and in each one of these cells, the traditional Gauss quadrature for triangles is considered. And for the new integration points, we need to adopt here a radius for the nonlocal region, and therefore define in which old integration points are going to be considered for this non-local average function. The state variables should be transferred. They vary according to the adopted constitutive model. When we have non-scalar variables, a different technique is considered, and we adopted here the closest point transfer technique according to Petsak and Gerais. The transferring method might unbalance the state variables in the element, but it is recovered in the next step of the incremental iterative process. It might need a few more iterations on it. In order to validate such propositions, we here present an L-shaped panel. This is its general configuration. We adopted a smeared crack model, and those are the material properties considered. This is the mesh with T3 3-node triangular elements, and the element medium size is 25 millimeters. For the solution process, we adopted the displacement control method, and those are some parameters for it as well. Well, in terms of numerical integration, for the conventional one, here mentioned as CI, we adopted 6 Gauss points per element, and for the subdivision of elements, here mentioned as SI, we adopted 3 Gauss points in elements not containing the crack, 3 Gauss points per triangular cells in elements containing the crack, therefore 9 points in total, and for the Gaussian function parameter, the radius r of the region A, this parameter is equal to 20 on this case. So this is the damage pattern that was obtained on the simulation, and we can notice that for the SI series, the damage pattern is better represented, and it's closer to the experimental results obtained by Winkler on this panel as well. These are the equilibrium paths for both series, and we can see a great agreement between the curves, and also that they have a lower peak than the experimental results. This is mainly due to the model that we adopted here once we consider the crack explicitly represented. Also, according to this graph, we can see the processing times of both series, and for the SI series, they have lower processing times throughout the process. Well, as conclusions to this work, we can mention that we proposed a new transferring technique to deal with the state variables history for physically nonlinear problems considering the XFEM framework, and also a numerical integration by subdivision of elements. We validated such technique, presenting coherent results and similar equilibrium paths, considering both conventional and the subdivision of elements integration strategies. As future studies, it's important to mention the expansion of the transferring technique to other damage models, and also the simulation of problems with such technique and considering the crack tip inside the element domain. This is the end of this presentation. Thank you very much for your attention.